Hello, this is Dr. Kraus with an intro to root locus video. The assumption here is that we have some plant, g of s, whose transfer function that we know, and we are trying to design a controller transfer function of some kind so that when we put the system under unity feedback, we will get a closed loop response that we think better meets our goals or is somehow improved by the feedback. Obviously, we're not trying to use feedback to make the system worse. The idea here is that we would have some gain k that we would ultimately factor out of the system, and we would want to predict, so big ideas. One, predict the closed loop pole locations based on the open loop transfer function. The idea there is that we do not want to have to find the closed loop transfer function, especially in a symbolic form, if some gain k is supposed to be unknown. So how do we predict the closed loop pole locations based on the open loop transfer function? And specifically, we'll talk about this more in just a minute, but we're talking about a loop transfer function. So not just the plant transfer function, but kind of the forward part of this control loop. And ultimately, we're probably going to factor some gain out of the controller. Now, it could, in general, be any parameter, but I'm going to make the assumption that we have some gain k that we're trying to design or solve for. And so we want to take our controller transfer function, factor out this k, and that is the loop transfer function whose root locus we are going to sketch. And the idea is we want to predict these closed loop pole locations, and specifically we want to track those closed loop pole locations as the gain k is varied from 0 to infinity. So ultimately, we'd like to use this to kind of choose the gain k after we have a form for d of s and we have our desired closed loop pole locations in all of those pieces. But the idea here is that once we had a form for d of s, we factored out the k, we would look at the root locus of L of s as k goes from 0 to infinity, and we would watch how the closed loop pole locations vary as we vary k. So let's next talk about how we take this block diagram and reformulate it into k and L. So assuming we started with this kind of standard form for a unity feedback meaning there's nothing in the feedback loop, control design problem, one important preliminary step before we're really ready to use the root locus method is to reformulate this into something that involves L and K. And we'll talk about why that's essential in just a second. But essentially, until we do this, we really aren't ready to use root locus. And I'll do two examples shortly for proportional control and PD control, maybe even a lead compensator, to talk about how we get into this special form. But if we're not in this form, we're not ready to do root locus. So why is that so critical? Let's talk about that now. The big idea is that if I had this form, then my closed loop transfer function for this system would be k times L over 1 plus k times L. And maybe if I wanted to be really careful, I'd make sure that wasn't L of s. So the big idea, the fundamental idea behind root locus is that the closed loop poles occur when 1 plus k L of s is equal to 0. There's another YouTube channel by a guy named Brian Douglas who does a really good job with a lot of this and has some really good root locus videos. He, for his purposes, likes to call this G instead of L. It means the same thing, so don't let that throw you off. I'm trying to use the same variables that we're using in the textbook that we're using in my class. But the big idea is I've got some K, and this is just a constant. It does not depend on S, and it is varying from 0 to infinity. And then it's multiplying everything else. And we're making the fundamental assumption that when we want to find our closed loop pole locations, we're trying to solve the equation 1 plus K times L of S, or whatever else you want to call this, equal to 0. This is the equation we're trying to solve. This is the equation that gives us the closed loop poles, and it is this K going from 0 to infinity that is affecting our closed loop pole locations, and we're trying to understand how it affects our closed loop pole locations. So that is the fundamental formulation of the root locus method. So if we need to get our system into this format to use the root locus method, how do we do that? I want to talk about 2 or maybe 3 cases. The simplest case is proportional control, and we almost don't need to do anything in that situation. So if I had some U, some gain Kp, my proportional control gain, and some plant, then in order to get into root locus form, I simply need to recognize that in this case, L of S actually is just the same as G of S. That's easy. And then the K that I'm talking about is just Kp. So I need to do almost nothing. And part of the reason for that is that the closed loop transfer function for this proportional control system would be Kp times G over 1 plus Kp times G. And so the, sorry, my paper's running into my laptop. So if this is my closed loop transfer function, then the poles, my closed loop poles, occur when 1 plus Kp times G of S is equal to 0. So this is the gain that I'm trying to vary, which we've been calling K. And then this is whatever multiplies K. So for proportional control, we essentially get it for free. L is equal to G, and K is equal to Kp. What if, instead, we wanted to do PD control? So how do I design a PD controller using the root locus method? So in that case, my D of S is Kp plus Kd times S. And so I'm assuming I still have kind of our standard form. So this with D and G as the names of my plant and controller, or controller and plant, is kind of always in my head. So having this, how do I find my D hat with K factored out? And so the easiest thing to do there would be to first rewrite this. I don't know why I'm doing this. So KDS plus KP. And then we want to pick a gain. It's generally slightly easier to use KD. So if I factor out KD, I could rewrite that as KD times S plus KP over KD. So I'm factoring a KD out of both parts of this, which I could then also rewrite as KD times S plus my 0 location, where Z is defined to be KP over KD. So if I have D is equal to KD S plus Z, then I could say that my K is just KD, and my D hat would then be KD S plus Z divided by KD, or just S plus Z. So, assuming I had some transfer function that I know for G, in this case, then L would become S plus Z times whatever the transfer function for G is. And then my K is just KD. And so we would be tracking the closed loop poles for this PD controller. we would first have to choose the 0 location before we could draw the root locus, and that might be a little bit weird. But it's just necessary. And you could then draw the root locus several times with several different choices of z and just kind of see how it affects the shape. But L would be s plus z times g, and k would be kd, and we would now be ready to do root locus. I sort of promised I would do a third example. Hopefully by now this is almost trivial. But if I had some lead compensator, to my mind that would already be in a form that has a gain factored out. So I would have some 0 location, some pole location as my d of s. And assuming that same block diagram format with d and g in the loop, let me just draw it really quickly, just so we're all on the same page. Slightly sloppily as a result of my quickness. But assuming this format, if I need to then factor out my gain, hopefully it's fairly obvious, that L would now become that times g of s. So this is my d hat of s, where d hat of s is defined to be my d of s divided by the gain that I'm trying to factor out. So hopefully it's apparent, and I don't know why my whole page seems overexposed or something with poor contrast. But s plus z over s plus p is my d hat, and this is the k that we're trying to design or choose or whatever. And so we end up with this L, and then k would just be k. And so I would choose my 0 and my pole location, multiply d hat by g, and then do the root locus of that, and just kind of see if my poles as a function of k move to locations that I like or not. And if not, then I could try different z's or p's, or maybe I would give up on the lead compensator and choose some other form. In my next video, I want to talk about how the open loop poles and zeros of L are the starting and ending point of the various branches of the root locus.